Hi, thanks for coming to my talk. My name is John Bodner. I'm a staff engineer at Datadog. I'm the author of Learning Go from O'Reilly. Second edition is coming out in January. It's been expanded to cover the changes in Go since 2021, including Go 122. Be sure to pick up a few copies for yourself, your friends, and what the heck, your pets also. This is actually my fourth time speaking here at GopherCon. That's my first time speaking in person since 2018. It's pretty great to be back up here and to see everyone. Today, I'm going to talk about a few topics: programming languages, DevOps, and some Go tools that you probably didn't even know existed. Now, these sound wildly unrelated, but over the next 40 or so minutes, you'll learn how to combine them to make both your Go code and your cloud environments easier to understand. Now, in previous GopherCon talks, I've called Go boring, and I've run a game show on weird Go corner cases. So people might think that I give our favorite programming language a hard time. So today, let's start a little bit differently. Simple question: what makes Go great? So I realize asking this at GopherCon is like asking people at Disneyland what makes princesses awesome. But still, I'm sure everyone here has an answer to this question. I'm the one up on stage, so I get to give my answer. And for me, what makes Go great is that it's a non-magical language. And what do I mean by non-magical? So this comes down to three things. The code is easy to read. When you read the code, nothing's hidden. You can see everything that executes. And when you compile, you get this native binary with no dependencies. And why is it so important that Go is easy to read? It's because when we write code, we are primarily writing it so someone else can understand it later. As Hal Abelson, the legendary CS professor from MIT, once said, programs must be written for people to read and only incidentally machines to execute. Now, very closely related to readability is that Go code doesn't hide things. It's pretty easy to figure out what function is invoked by what function in what order. And that's one of the reasons why there's no method or function or operator overloading. And finally, when you're ready to ship out your code, you get a single binary that's easy to package up and ship out. You can put it into a scratch Docker image. You can put it into a zip file and email it. You don't have to worry if the person has a virtual machine installed or a certain version of a shared library. It's all just very self-contained and easy to distribute. And these three things are pretty great. They've helped me to avoid a lot of pain whenever I'm working in Go. Magic in programs often seems like a great idea when you're working on it, but when you go back to the code later or have to debug a problem, it's always like 10 times harder to figure out what's going on and what went wrong. But, and yeah, there's always a but, there are some downsides to the things that make Go great. And before I go into those downsides, let's change topics for a moment. Let's talk about distributed tracing. Now, I promise this will all make sense in a couple of minutes. So like I said, I work for Datadog, and what we do is make it easier for companies to understand their cloud environments by gathering data about it and making it searchable. And there are open source projects and competitors, but in the end, there are three main sorts of data that are gathered to understand infrastructure: logs, metrics, and traces. I think everyone here is familiar with logs. You know, we've all used them. Developers put log statements at important points in their code to track what's going on, provide some important clues when things inevitably go wrong. Now, logs are relatively easy to capture and process. You just send the file or system output to a server, you index the text, you've got some basic understanding of your applications. And because you're looking at a data source that developers create themselves, logs are a good foundation for a monitoring system, but they're actually often the least useful bit of telemetry. So logs are often like scar tissue. They tend to be in the parts of your program that have problems in the past. And that might be useful information in the future, but unless you're very methodical, logs don't give a complete picture of what's going on in an application. And also, unless you've put in the effort to structure your logs via JSON or some other formatting language, they might be hard to parse apart, or you have inconsistent names for the data fields in there. And so metrics are numbers that describe your computing environment. This can be things like CPU speed, disk space free, number of simultaneous network connections. Whatever numbers can describe what your programs are doing, that's what metrics are. And some metrics can be gathered from your computing environment. Some come from third-party tools you've integrated with, and you can add additional custom metrics by adding some code to your application. And because much of this information comes from your environment, you get many of the most valuable metrics for free. Just install a piece of software in your environment, and you get lots of information that you can look at in pretty graphs in your monitoring application. The downside to metrics is that, well, they're numbers. Some numbers might be pretty clear. If you have no incoming requests for a microservice in production, that's probably a bad thing. But other numbers, they're more ambiguous. Is high CPU usage or high RAM usage good or bad? How many incoming connections are too many? What's a good response time? Now, furthermore, metrics may tell you what is wrong, but they often don't tell you why. In today's complicated cloud environments, relying on metrics alone makes it hard to figure out what is wrong. If you have that application with no incoming requests, how do you know what other applications normally call it? If a service is using lots of RAM or taking a long time to respond, why is that happening? And that brings us to traces. Traces show the flow of data within and between the components of your system. And a trace contains one or more spans. And a span is some section of interesting activity in your program, like receiving an HTTP request, or calling a database, or making a gRPC request, or just a section of code that takes some time to run. Now, traces become really valuable when they're distributed traces, and that's when you can track an individual request as it goes from server to server, seeing what data is passed along and what comes back. So traces sound really useful, A plus data. But how do you gather that data? So the most obvious way is a lot like adding logs to your code. You go to important points in your program, like where the HTTP requests are being made or where they're received, and you add some code to capture them. And there's an open standard for adding traces to programs called OpenTelemetry. You put functions and methods it calls into your code, and this works across multiple languages. So here's what creating a trace in a span looks like in Java. Don't worry about the details, just marvel at the amount of code that you need to write. Here's what it looks like in JavaScript. And since this is GopherCon, here's what it looks like in Go. So first you have to set up all your tracing. Once it's set up, you put code like this into every single function and method that you want to instrument. Now, that can be a lot of code to write. And you have to make sure you properly close your traces and spans or you get weird errors and broken traces. To avoid this sort of work, Java developers use annotations to reduce the code down to a single word. Just put @ with span before a method, and the start and end of the method automatically maps the start and end of a span. And when the code loads at runtime, an annotation processor sees that annotation, generates code from it. And there are similar features in other languages. Python has decorators, and they provide similar functionality. But in many popular programming languages, you can use magic to go even further. You get traces and spans by adding no code at all. So rather than modifying the code developers write, libraries get added to a program at runtime by modifying the command line. And these libraries analyze programs while they're running and put in trace information automatically. Here's how it works in Java. This Java agent that intercepts classes as they're loaded, it rewrites them to include tracing information. In Node, you have a require to import a library, does something similar. And in Python, this wrapper program is launched to set up similar behavior. And this gives you pretty good basic coverage of what's going on in your programs and how they're connecting to each other without the developers of your company having to write a line of code or even finding out that their programs are being instrumented. Now, for languages that support annotations, you combine them with that automatic instrumentation, and you get very easily and non-intrusively, you can add detailed tracing to your applications. And that takes us back to Go. Remember my list of the 3 things that I think make Go great? Well, the things that make Go great, that lack of magic, are the exact same things that prevent us from intercepting code at runtime. One of the things that makes Go easy to read is the language simply doesn't have all that many features. The closest thing Go has to annotations are struct tags, but you can't put those on functions or methods. Even with struct tags, though, there's no way to automatically run code that processes them. Annotations are automatically processed in Java by that Java agent. The virtual machines that run Java and Python and Node, they give a place where code can be intercepted before it runs. And since Go programs build to a native binary with no dependencies, there's no good way to insert code into a Go program after it has been compiled. And this means that unlike Java or Python or Node, where you can add trace support to a program after it launches, Go requires you to put trace information into your Go program when it's compiled. Now, putting trace information into your code is certainly in the spirit of nothing hidden, but it makes your code harder to read because your business logic, the code that gets things done, the code that earns you money, is now mixed with the code to monitor your system. So in short, that magic in those other languages, while it often does lead to debugging trouble, in this case, I have to admit that it's pretty handy. So maybe we can borrow just a little bit of magic to make it easier to add traces to our Go programs. In the Go ecosystem, we use tools to provide magic instead of language features. Now, some of you may be aware of eBPF, which is a very exciting technology that lets you run sandbox programs inside the Linux kernel. There's a GitHub project that is currently in an alpha state that uses it to implement magical Go auto-instrumentation, but it has some implementation details that makes it a little bit scary to use in production. I don't want to say bad things about another project. I'm happy to talk about it afterwards. I am very interested in this effort, though, and I'm watching to see where it goes. So at Datadog, we took a different approach, and it's called Orchestrion. It's a tool that automatically adds tracing information to your source code before you compile it. And before I talk about how Orchestrion works, let's break this problem down, and I'll make this as simple as possible. We're only going to create 3 kinds of spans. A span started when an HTTP client is used, a span started when an HTTP server receives a request, and a span that maps to a specified function. So what we want to do is detect registered handlers, detect net HTTP clients, and detect specially marked functions. And for the specially marked functions, we want to do 2 different things. First, we want the ability to mark a function as being the start and end of a span. Second, we want to be able to mark a function as saying, don't process anything inside of it. And let's add a couple more requirements. Let's give some options for our tracing output. So the goal is to send our traces to a monitoring system, but it's nice to be able to test locally just by sending information to the screen. So we're going to make our inserted code flexible. When we insert the code, we can choose to either insert open telemetry support or simple print statements. And one more thing. If we're inserting changes to source code, we also want to be able to remove it. Being able to clean up after yourself, it feels like the neighborly thing to do. So these requirements might seem tricky, but it turns out that Go has a couple of sparks of magic hiding in its tools. You just have to know where to look. And before we see how it's done, let's jump to the end and look at a quick demo of Orchestrion in action. The services I'm going to show off don't do anything interesting. They're just there to generate traces and spans. And so you have your mod file, and you have a first server with 2 endpoints in there. Second server called by the first, and again, no instrumentation. And now we're going to run instrumentation by calling orchestrion-w-target-otel. And now you can see the instrumentation has been added to the code. And there it is in server 1 as well. Nothing in Go mod yet, so you run go mod tidy. And there are dependencies. And now we're going to build our servers with go build. And we're going to launch them. And now we're going to hit 2 endpoints in that first server called in and think. And there's a copy of Jaeger running in the background. And you can see after I reload the screen here, we can find the traces, and there they are. Here's the first trace. And here's the second one, it's the distributed trace that called both servers. And then we can go back to our code, run orchestrion-rm-w, and the instrumentation is going to be removed. So you can go back and look at our source code again. No more instrumentation. And we'll run go mod tidy one more time. And we're back to our original state. So how do we do that? So let's start by diving into the concept of a parse tree. So quick show of hands. How many people here have written a compiler or interpreter before? All right, pretty good number. For the rest of you, you might be wondering how a compiler goes from source code you can read to a binary that the computer can execute. And this is a multi-step process. We're not going to talk about all of the steps, just the first 2. So let's start with a simple program that we have on screen. When a compiler processes source code, the first thing it does is break it into units called tokens. A token is just the smallest part of a program. It can be a number or a keyword or a function or variable name. And here's a list of some of the tokens that are found in this sample code. And as the computer is tokenizing your program, it's also parsing it, which simply means discovering its structure. A parser takes those tokens and builds what's called an abstract syntax tree, or AST. And each token in your program becomes a node in the tree, and they're all organized with additional nodes to help define the structure of your program. So as you may know, the Go compiler is written in Go, and its code is part of the standard library. So you can find an AST builder in the standard library in the Go AST package. And it works with the parser in the Go parser package, and a tokens in the Go token package. And it's great that we have this AST builder available, but it has a serious drawback: comments. So comments are kind of a gray area in a program. They aren't part of what runs, so they seem very ignorable by a parser. And it turns out that Go AST has a problem here. It doesn't handle comments very well. And there was a GitHub tracking issue that was filed about this about 6 years ago. Rather than associate a comment directly with a node in the AST, it's like associated relatively with the line number. And this means that if you make a change to the AST, insert a line or a comment, all the comments below that line need to be recalculated. And it is technically possible to do this, but it's just not all that practical. But luckily, the great Go third-party library ecosystem comes to our rescue. Dave Brophy has written a modified version of Go AST called DST, and you can find it up on GitHub. It has great comment support and other nice features like automatically inserting dependencies when you convert the DST back to source code, and that's a hint for where we're going with this. And we can use the apply function in the DST-util package in the DST module to go through the program, spitting out each token that we come across, and we can see the structure of the resulting tree. So let's see how some of those lines of code get represented by an AST. The main function declaration is represented by a funcDecl node. It has an ident node with the value main, a funcType node, and a block statement that has the body of the function. A funcDecl is also used to represent a method, so if there was a method, receive would be assigned a value. So let's go back and look at that funcType node one more time. It has a field list, which are the parameters of the function, and since main has no parameters, we have an empty field list here. There's no return values either on main, so results is nil, and main has no type parameters, so type params is nil as well. The call to HTTP handle func is represented by a node of type expression statement, which contains a node of type call expression, and the call expression contains a selector expression node with the two parts of the function name, HTTP and handle func. It also has the parameters for the function call. The /lit is a basic lit node, a basic literal, and the anonymous function is a funclit node, a function literal. The anonymous function that we are using as our handler is probably the most complicated part of this little program. Just like our main function, it has a funcType. In this case, the field list has two fields, the HTTP response writer and a pointer to an HTTP request. And also like the main function, it has a block statement node hidden by the captions, and that holds the statements for the body of the function. So the body of the anonymous function should be pretty easy to follow now. It's an expression statement node, has a call expression node, that has a selector expression node, and that names the method, and there's a second call expression node for the parameter to the RWWrite method. So what's interesting is that the AST uses a selector expression in this line to represent a method name, RWWrite. On the previous slide, a selector expression was used for a function name, HTTP handle func. So most of these nodes in the tree have dual purposes, multiple purposes. Call expression can be a function call or a method call or a type conversion. And an array type can refer to either an array or a slice. Later stages of the compiler are able to resolve these differences, but as you'll see, Orchestrion works without any of that additional information. And we can even round trip from our source code to the AST and then back again to source code by creating a decorator and calling its fprint method. And that's how to solve this problem. After converting a program to an AST, you modify the tree, inserting code in just the right spots to provide some new functionality. And that means we can take a source file and look for things like net HTTP clients and handlers. We find them, we insert some code that adds tracing support, and then turn that modified AST back into source code. And to specially mark a function so it can be used as the boundary for a span, we can use a small bit of magic. There's already a pattern for this in Go. Anyone know about Go compiler directives? You put in magic comments like go no inline before functions to give hints to the Go compiler. And so let's try out that same idea to give hints to Orchestrion. What we can do for Orchestrion is to mark a function using a comment that starts with dd_span. Developer can put this comment before the function, and Orchestrion can scan for that comment. And when it's found, Orchestrion can then modify the source code to include the span handling that normally would have to be written out by hand. And similarly, we can ignore a function by looking for a different comment, dd. So how can we clean up the code? Well, we need to know what code was inserted so it can be removed later. And to do that, we can put a comment right before the inserted code and right after the inserted code. And that makes clear what's changed and makes it easy to automatically remove it later. So now that we have our techniques, let's see what it looks like to modify a program. I'm skipping over the code that reads in files. We can focus on the code in Orchestrion that walks and modifies the AST. And in all these code samples, I'm going to remove the error handling just so the code all fits on the slides. So we start by using this parse file function in the Go parser package, and that builds a Go standard AST out of the source file. And then we convert it to the DST package using the decorate file method. Next, we're going to loop over all the top-level declarations in the file, which are in a slice called decals. And this includes import declarations, function and method declarations, constant and variable declarations. Right now, we care about function declarations. So we use an assertion with our friend funcdecal there to check if the current declaration is a function declaration. The very first thing we're going to check for is the easiest, doing nothing. So let's see how to implement ignoring a function. We're going to list of the comments before the function using the decorations method on the declaration and pass a list of comments and the constant dd_ignore and use this hasLabel function to see if there's a comment line that matches the label that's passed in. If there is, we just ignore the function, continue the loop with the next declaration. Next easiest thing to look for is a function or method that we want to wrap with a span. And if we find a comment that starts with our dd_span constant, we call add span code to function and reassign our declaration with the value that it returns. So let's dive in a bit to that add span code to function so we can see what AST hacking looks like. The first thing we do is see if the function has already been instrumented. We grab the comments attached to the first statement in the body, and if one of the comments starts with dd_start_instrument, this function was instrumented in the past, and we can just return without doing anything. So you can see why having comments is so important for Orchestrion. It allows us to not only make some magic annotations, but it also lets us avoid re-instrumenting the code. So we're also going to gather some data that we're going to report for this span. So we can take any space-separated words after the dd_span comment, and we save them off so they can be tags that get attached to the span as additional information. We also grab the name of the function because that seems like really useful information to include in a span as well. Next, we're going to find the context parameter. One additional requirement that I should mention, in order to wrap a function in a span, that function needs to have the context as the first parameter. So the context is how you're going to pass trace IDs and span IDs along from span to span and process to process. And there actually are some really terrible tricks you can do to avoid this, but we are trying to keep the magic to a minimum. So if you're curious, ask me about those tricks afterwards. So we look for the context in the first parameter of the function by using the isType function to check the type of the parameter. If it's there, we store the parameter's name so we can use it later to build some new nodes. If it's not there, we exit. We're unable to instrument this function. Now all that's left is actually building our new instrumentation nodes, adding them to the body of the function, and then returning our updated function declaration. And the building happens in that build span instrumentation function. And before we look at the code and build span instrumentation that generates the nodes, here's the code that Orchestrion's going to insert. It's just 2 lines of code wrapped in 2 comments. And I'll talk about what that report function does in just a little bit. And now that you've seen this, here's what the code to insert it looks like. That's actually a lot, and actually it's only half of it. This is the code for just the first line. So I'm going to break this down over the next few slides so it's easier to understand. This function returns a slice of type DST statement, with each in the slice representing 1 line of source code. So we're going to insert 2 lines. Each line has 1 comment attached to it, so there'll be 2 entries in this slice. DST statement is an interface, and there are many statement types that implement this interface. We're adding an assignment statement, which is represented by a pointer to DST assign statement. It has 4 fields that we need to set. There's LHS, which is the left-hand side of the assignment, toke, which is the operator used for the assignment, RHS is the right-hand side of the assignment, and dex are the comments on the assignment statement. At the top of the screen, you'll see the code that we're going to insert. I'll highlight each part when I show the AST representation for it. So we're going to start at the end because actually that's the most interesting part. The right-hand side of the assignment statement consists of a call expression, which is a call to the function report in the github.com John Bodner or Orchestrion instrument package. Report function, it takes in a context, an event type, a function name, and a list of key value tags. And then it then calls the underlying tracing library, whether it's OpenTelemetry or Datadog or the console, and uses that to mark if it's starting or ending a span, and then it returns a context as a trace or span already in the context. The AST nodes represent the parameters of the report function, and they're built by calling the build_args function. You pass in the context info that we created earlier. We pass in a constant to indicate, in this case, this is the start of a span. We pass in the name of the function and any tags that we found on that dd-span comment. Next, we see how to attach a comment before a statement. We assign to dex a DST assigned statement decoration with the start instrument comment that you want to add. And now all that's left is the left-hand side and the operator, and that's pretty simple. We're assigning the context returned by instrument report back to the context variable, and the operator that's used to assign is an equal sign, which is represented by token.assign. So for the sake of time, I'm going to skip over the code to add the second line, but it's pretty similar. And this has been a lot of code, but with these changes, we basically have the exact same functionality as that with-span annotation in Java, and that's pretty great. So let's see how to instrument HTTP handlers next. In order to instrument an HTTP handler, we have to find the places where a handler can be registered. And there are a few options in Go. So for example, you can have an HTTP server instance where you have the instance being created. And to instrument that, we're going to insert comments before and after the handler field and wrap the handler call in a call to wrap handler function, which is in Orchestrion's instrument package. There's also a HTTP handle and handle func functions in the standard line. And we're going to insert comments before and after each line, wrap the handler in a call to wrap handler or wrap handler func. And finally, there are the handle and handle func methods on an instance of an HTTP serve mux. And just like the functions in the net HTTP package, we're going to insert comments before and afterwards, and then wrap the handler and calls to the wrap handler func functions in Orchestrion's instrument package. So how does Orchestrion replace a handler? Remember that AST node tree from earlier that represented a call to HTTP handle func? So we look for an expression statement that has a call statement that is a function with two arguments, where the selector is handle or handle func. We then take the second argument, wrap it in a call to instrument wrap handle or wrap handle func. And when Orchestrion finds the statement, it wraps it in comments, and then wraps the second argument for the function in a call to wrap handler func. To support the handler field in an HTTP server instance, there's more AST walking. And here's the AST tree. Orchestrion looks for an assignment statement, and if one is found, it checks if the type of the right-hand side is HTTP server. If it finds one, it then iterates over all the fields. And if it finds a handler field, it wraps that value in an instrument wrap handler. And here's the code to do the wrapping. Start wrap and end wrap comments are added around the field, and then you change the value assigned to the handle to the wrap handler function, and then pulling out the value that was originally assigned to that field. And wrapping an HTTP client is similar to wrapping a server. We're just looking for places where an HTTP client was instantiated, and instead of wrapping a field inside of that instance, we wrap that whole value in our own wrap HTTP client function in the instrument package. And there's also the code for removing existing instrumentation. I'm not going to go through all of it, but I'll show some of the code to remove HTTP handlers. It's a lot like the code for handlers in the first place. You iterate through the nodes of the AST, looking for an expression statement that has a call expression with more than one argument that calls either handle or handle func, and whose second parameter is a call to wrap handle or wrap handle func. And when you find that, you take that argument to wrap handle func, and you just make it the argument to handle func. And this is the code to do the unwrapping. Orchestrion checks if the second argument to the function call is a call expression, and then checks if the second argument is a call to wrap handle func. And if so, it takes that argument of wrap handle func, to the calling function, just out of the AST tree. The code to remove comments isn't shown here, but they're removed by simply looking for the start wrap and end wrap comments and removing them from the list of comments on the node. So once you get the hang of this AST hacking, it's not hard, it's just a little bit tedious. And there's still the matter of initializing our tracing libraries. We have one last thing to do when scanning for functions. If Orchestrion finds a main function in the package main, it inserts a package-level variable called Orchestrion target, and has a call to instrument init as the first line of main, wraps both of those in comments, and Orchestrion target has its value set to the type of instrumentation that we're going to use, console, OpenTelemetry, or Datadog. And this variable is then passed into instrument init, and I'll explain why it's done this way in just a little bit. And with all this in place, you now have a command line tool that can automatically add trace support to your application's code. Simply install Orchestrion, run it against your code, update your dependencies, commit your changes back to source control, and build it. And if you want to remove the instrumentation, just call Orchestrion again with -rm, update go mod, commit your code back to source control, build it again. So as you've seen, Orchestrion always wraps the calls to the instrumentation target rather than put console or OpenTelemetry calls directly into your code. And this makes it much easier to both insert and remove that instrumentation, decoupling the target from the code itself. But you might wonder why I bother with that package level variable. And that leads to the next little bit of magic that we can get from Go's tools. Sometimes it'd be nice to switch back between writing to the console and writing to a tracing backend. So, for example, you're a developer and you want to test your code out locally. And you don't want to have to set up a OTel collector every single time you run an end-to-end test. And we can control that with another little-known feature of the Go build tool. So Go lets you override the value of a package-level variable at build time using the flag -ld flags -x package name var name equals value. You just need to run go build with this flag set to console, and now you have a build that writes spans to the console. Build without that flag, and your spans are now sent to the OTel collector. And if we added that Orchestrion layer of indirection to the code, instead of putting the OpenTelemetry or console calls directly in there, we can now choose which ones we're going to use at compile time. Or as David Wheeler, the first person in the world to get a PhD in computer science, once said, all problems in computer science can be solved by adding another level of indirection. What if we want a little bit more magic? So we can hide our instrumentation using another little-known Go build flag. Have you ever actually looked at all the Go build options? There's over 30 of them, and some of those flags have sub-flags. So today we're interested in one in particular called tool exec. Under the covers, what Go build does is it calls a lot of other tools to do its job. And the tool exec flag lets you specify a program that runs each of those tools that Go build uses to build your code. In short, it lets you specify a preprocessor. So if you set the -t flag in Orchestrion and supply the current working directory, Orchestrion can be used as a tool exec parameter. And when you run Orchestrion in this mode, the instrumentation is inserted into your code just before it's compiled, and you never see it in your program at all. So let's take a command line that's run for a tool exec tool. And, well, that's something, right? But let's take this apart and talk about the things we care about. So the tool we care about is the compile tool. Compile gets called for every single package in the standard library, third-party modules that you're importing, your own code. All of them are passed to compile in dependency order. Now, normally it's called directly, but when we add our own tool exec command, it's passed instead as parameters to this command instead. And here's what it looks like when we get to one of our own packages. So the first 3 parameters, Orchestrion -t and dot, are the commands that we specified with the tool exec parameter to go build. The rest of the line is the compile command line for this package. And we can ignore most of this line right now, but it ends with a list of Go files that we're going to examine. So it's actually a little bit tricky to find documentation on how to write a tool exec tool. So here's what you need to do. So first, Orchestrion looks at the command line that it's been called with. It looks for the tool name and checks if it's compile. There are other tools like ASM and link. Don't care about those. So next, we're going to create a temp directory. Any files that were modified will be written to a temp directory, and the arguments passed to compile will be changed to look for source code in that temp directory instead. The temp directory is deleted when Orchestrion exits, making the changes invisible in the source code, but present in the compiled code. And when Orchestrion finds a compile is compiling a Go file in the project directory, it instruments the file, writes the output to a temp directory, and then puts the new file name into the new args. Every other argument to compile tool is just copied directly into new args. And then finally, Orchestrion runs the tool that was passed into it. And if Orchestrion modified the command line, modified command line is assigned to args before you run the tool. And that's it. Everything you need to do to implement your own Go build preprocessing tool. So there are 2 small drawbacks using tool exec to modify your code. The first is that -a flag in the Go build command. That's another build flag, and its job is to ignore any existing cache for your source code, both yours and third-party code, and then instead rebuild everything from scratch. And if you don't do this, the program specified by tool exec won't be run on source files that haven't been modified since the last compile. So this does make compilation slower, but the Go compiler is pretty fast. The other drawback is you do need to add one line to your code in order to get tool exec to work correctly with Orchestrion. As I mentioned, Go code is compiled in dependency order. Before a package, every package it depends on must have already been compiled. And since we're inserting code from Orchestrion's instrument package into our program, you need to make sure Orchestrion's been compiled before those packages get compiled too. So the easiest way to do this is to add a single line to a file in your main package. Just import _github.com, John Bodner Orchestrion instrument. A blank import is normally used to trigger an init function in a package, but in this case, it's just there to make sure Orchestrion's code's been compiled so the rest of compilation will work. So now we've got two options for developers. They can either make the changes visible by running Orchestrion and committing the modified code to source control, or they can run it as part of the build command, keep the traces invisible. So the trade-offs are how comfortable you are in your team with magic, the need to add that single import statement to your program, and the time it takes to rebuild the entire code base. So far, we've just instrumented the basics, but we want to instrument third-party libraries too, things like Chi or Mux or Echo, and we can keep on writing code like we've done for HTTP, but it's tedious to maintain all that AST hacking by hand, especially as you add support for more things like gRPC clients and servers or Redis or database SQL. It'd be nice if you had something a little bit higher level. And there is actually something like this already in the Go standard tools. Another quick show of hands. Who's used GoFump before? Yeah, just about everyone, right? But there's another GoFump. In the standard Go distribution, there's GoFump with a space and GoFump without a space. So first of all, who knew that both of those existed? All right, some people. Did you know it can rewrite your code for you? For example, if you execute this line, GoFump finds every place in your code where there are unnecessary parentheses, and it removes them. And so the source code for GoFump is in the standard library. You probably wouldn't be surprised to find out that it works by using AST library to pattern match an existing source file. So GoFump and similar refactoring tools are kind of inspiring. It'd be nice to specify something like a get method for Chi or Echo and wrap that with a span, just like we did for the code that's registered with a built-in HTTP MUX. So let's use that inspiration of GoFump to make Orchestrion a little bit better. Let's start by describing what we're going to do. So first, we're going to create a rule file that describes the transformations. Then we're going to write a program that parses those rules, loads a Go source file, and then applies those rules to the file. And I'll start with a rule file that supports Chi. It has two parts. This is the first part up on the screen. One part lists the functions and methods we're going to rewrite and what the rewrites look like. So we're looking for functions or methods, look like the expressions on the left-hand side of the arrow, before the arrow. And we're going to convert them to the expressions that look like what appears after the arrow. Other part of the rule file just names the placeholder parameters and gives their types. This provides us a way to make sure that we're transforming the right functions and methods. Since it's possible to have the same method name on multiple types, you want to make sure that we're only transforming the correct methods and functions. And you do that by, you don't pay attention to the package or instance name, but you match the function name, number of parameters for the function, and that the parameters are of the correct type. So how do you parse that rule file? Well, you use Go's parser and AST package, as well as the DST module. And there's a function in the Go parser package called parsed expression that generates an AST from an expression. And you take that placeholder list, you use parse expression to convert the type of the placeholder into a node, you convert it to a DST node, and you add it to this map where the key is the placeholder name, the value is the node. And for the production rules, we do the same thing. We convert the before and after expressions into DST nodes. And then there's a little processing to extract some function names and arguments. And then we build a rule out of that information. And once we have the rules parsed, we just walk through the source code. And we're only going to solve for replacing function calls. This code's pretty simple. We're looking for our old friends, a call expression node that contains a selector expression node. And every time that we find one, we try every rule, see if it works. And check apply rule checks to see if the function name, the parameter length, and parameter types match. If they don't, we exit. If they do, we continue. We then update the arguments to the function by making a new argument list and then populating it with the parameters specified in the after rule expression. And that DST clone line is there because a tree can't contain the same node more than once. So every time that we insert an after rule parameter node, we have to duplicate it first. Finally, we wrap the line with start instrument and instrument comments, just like before. And running it against this code here, it gives this result. There's our instrumentation. And the code for the rule parsing is simpler than what we had to do before because it doesn't depend on any of that hard-coded specific function names or package names or types. We're just matching expressions in the existing source code against our left-hand side, and then replacing expressions with the right-hand side, moving the placeholders to the correct locations. We're just working with nodes in a tree, reorganizing it to implement our features. In fact, this might be the first time that all those leet code questions on trees are actually put to good use. So this technique, putting together AST parsing and using comments for annotations, using toolexec, there's a lot of places you could go with that. And in fact, it's a doorway to add a lot of magic to your Go programs. But really, you have to be careful with your magic. You want to avoid problems with things like Java annotations, where you can lose track of how your code's being modified and how your program's data is flowing and how that data is being transformed. So if you do want to stick to the spirit of Go, what can you do with these tools? So here's something I've been thinking about: contract programming. If you're not familiar with the concept, the idea is that the functions in your program check properties of the input parameters and the return values. So Go is a strongly typed language, and that allows us to check types at compile time. But there are properties that you need to enforce at runtime, usually because they involve data that you're reading into your program. And this can be security issues like access checks or data validation checks. And the code for these is often repetitive, and it's in multiple parts of your code, like tracing and logging. These are cross-cutting concerns. And because it's not core to business logic, it's easy to forget to add or update these, and that leads to bugs. So using annotations via magic comments and AST parsing, or writing rules to find the code that needs protection, that automates the way that works and makes it hard for it to be accidentally missed. So in the end, Go does remain a non-magical language. It replaces the magic in other languages with an amazing set of tools. You have things like AST manipulation, package variable overrides, toolexec, and automatic refactoring tools like GoFumped. And we've used them at Datadog to make it easier for our customers to add tracing to their Go code. So what I've shown today is a stripped-down version of Orchestrion and how it works. The full version supports database calls, gRPC, some third-party libraries, and it puts in trace and span support for Datadog's native tracing API. The replacement language in toolexec, that's something new we're experimenting with, and we're hoping to use it to quickly add support for some new popular libraries. And like all open source projects, it's a work in progress. We would hope you're interested in using it and contributing. Bet developers at your company and your customers, they could also benefit from taking advantage of these techniques. Thanks for your time. Enjoy the rest of GopherCon. I hope you go forth and do a little bit of safe magic of your own.